Today we will discuss boundary conditions for electrostatic fields, in which we will see how electric field will behave in this dielectric, conductor-dielectric and conductor free space interface. So when we have these boundaries of different mediums, and we know electric field in a particular medium, we can easily find out value of electric field in another medium by using these boundary conditions. So we will start with this first dielectric medium interface, and here we have assumed two medium 1 and medium 2. As you can see, we have two mediums. One is written here, so this is first medium, this is second. The permittivity of this medium is epsilon 1, and this is for second medium is epsilon 2. So if we want to study any, let us say we want to study electric field, so we need to study at the interface two component, tangential component and normal component. So this ET is tangential component and this EN is normal component. So in these two mediums, you can see this is the resultant field E1. This is vector sum of this E1T tangential component in this medium and normal component in this medium. Similarly, in the second medium, this will be equal to E2, and this E2 is algebraic sum of this tangential component and normal component. Now remember this simple trick. To find out this tangential component, we always use this curl of that field. So we are here dealing with electrostatics, so we will use curl of electric field will give us tangential component. We know that this del cross E is equal to 0. This is the differential form. If you want to write integral form of this, you can write this A dot dl is equal to 0. Now if you want to find out this normal component, always use this divergence of that field. So del dot E is equal to rho by epsilon will give us normal component. And if we want to write down differential, so this is the differential form. If you want to write down integral form, so that will be equal to d dot ds is equal to q, total charge enclosed. So here, this is the interface of medium 1 and medium 2. Okay, and we have assumed this closed surface A, B, C, D, A. So this closed integration on the surface A, B, C, D, A. Now we are assuming here this wave is entering from this part and going in this direction. So entering in this E2, this is E1. And another assumption is delta H is approximately 0. So if delta H is approximately 0, so if we are taking this tangential resultant here, so you can write here this A dot dl on this ABCDA closed path. So you can write this E2, and what is this value? Delta W from C to D. And what is this in the above? That will be E1, and the direction is opposite, so you will write minus delta W. Okay, this delta H is 0, then so that will be equal to 0 because E dot dl is equal to 0. So if delta is equal to 0, only tangential component will remain. Okay, no, this normal component is not there, because this normal component is corresponding to this delta H. So you can write here E2t delta W minus E1t delta W. So we can write here E1t is equal to E2t. Okay, so I am writing it again. Some misprint is here. E1t is equal to E2t. So you can write here like that. And also this is in electric field intensity term. We can also write, because this permittivity in medium 1 is epsilon 1 and in medium 2 is epsilon 2. So we can also write, this is also true, epsilon 1 is equal to E2t epsilon 2. So this is also true. Now you can see this tangential component of electric field is continuous across the interface. Okay, no change in this tangential component in the dielectric media. Now we need to find out this normal component. For normal component, we assume this type of surface. This is called as pillbox. Pillbox surface, and this is basically cylindrical Gaussian surface. Now here, let us see again, the wave is entering from that interface. So here, this is the interface here. So we will discuss that part only. This is the interface. So wave is coming from in this direction. So if this is D2, okay, so where will be its normal component? Normal component is like in this direction. So that will be equal to A and 2 normal component direction. Okay. Now if it is going like that, this one is D1. Okay, this one is D1 from that to that part. So where will be its component? So it is going in this direction, so its normal component will be like that, A and 1. Now so by using this Gauss law, we know that this d dot ds is equal to q. So we will write this q later on. So that will be equal to, so q will be equal to what? Rho s is a charge density here, and the surface area is delta s. So this is delta s. So how we can write this d dot ds? Now in this region we have this d2 and the normal component of this d1. So you can write here d1, sorry, d2 dot product with this a and 1, plus in this medium we have this d1 and this dot product with a and 2. Okay, so this is how the surface, and this for the surface delta s. So this d dot ds for this pillbox is like this. We can write like this. That will be equal to what? Rho s delta s. Now we know that from this geometry, this an1 is equal to minus an2. Okay, so put the value here. So it implies that put the value here, that will be equal to an2 dot d1 minus d2 delta s. Is equal to rho s. That will be cancelled out, and you can write this an2 dot. So that will be vector because it has direction. d1 minus d2 is equal to rho s. Or simply you can write this, because that will give us normal component, not the tangential component here, because of that surface. So we can write this d1n minus d2n is equal to rho s. So this is the value of normal component. So here the normal component of this electric flux density d is discontinuous across this interface, and this amount of discontinuity here is equal to charge density. Okay, so now let us say we have assumed these two mediums dielectric, and if we assume here, when these two dielectrics are in contact with no free space or no free charge, you can say, at the interface, if the no free charge exists at the interface, then this rho s is equal to 0. So you can write dn1 is equal to d2n when this rho s is equal to 0. So this free charge at the interface is equal to 0. So you can write this. So in short, we have found that this tangential component is continuous across the interface, and this normal component is discontinuous across the interface, and discontinuity is given by charge density. So this is how this electric field intensity behave for dielectric interface. So these boundary conditions are used to find out the behavior of electric field at the interface of two medium. Now, beside this, it is also used to determine the refraction of electric field across the interface. Now, see this figure. In this, we are going to study this behavior of this reflection at the interface. So this is medium 1 again, permittivity epsilon 1, medium 2 permittivity epsilon 2. So wave is like that. This is E2 as well as D2, because this D is equal to what? Epsilon E. So they are on the same axis. So E2 D2, that will be combination of this normal component and tangential component, and this E2 and E1 are making angle this theta 2 theta 1. Okay, with a normal to that interface. So this is a normal to that interface, and they are making angle theta 2 and theta 1 respectively. So here we can write here, we know that this tangential component are continuous across the interface, so E1t is equal to E2t. And this, what is this E1t? If this is theta 1, this is theta 2, so what is this E2t? So we can write this E1t is equal to what? E1 sine theta 1. That will be equal to what? E2 sine theta 2. Okay, from this is the theta 1, this is theta 2, so we can write this. Mark it as 1. Let us say this is equation 1. And this, now if there is no charge exist at the interface, if this rho s is equal to 0 at the interface, then this normal component can be written as like that, d1n is equal to d2n. And for this, so what is this d1n? You can write this epsilon 1 e1n is equal to epsilon 2 e2n. And what is this e1n and e2n? So this is e2n, and where is this? This is e1n. So you can write this epsilon 1 e1 cos theta 1 is equal to epsilon 2 e2 cos theta 2. So now let us assume this is 2. Divide this 1 by 2. So you can write here, you can divide this e1 sine theta 1 divided by epsilon e1 sine theta 1. So you can write here sine, that will be equal to tangent, okay, or you can write this tangent theta 1 divided by tangent theta 2 is equal to epsilon 1 epsilon 2. So this is how this is the law of refraction of electric field. Now let us discuss this dielectric and the conductor interface. So as you can see in this figure, we have a dielectric here, and this second medium is conductor. We know that this inside a conductor charge density is equal to 0. Now due to this charge density, because if you put any charge inside the conductor, it will move and redistributed on the surface to make this charge density is equal to 0, and therefore this electric field intensity is equal to 0 inside a conductor. So we will start with this. So inside a conductor we will not have this component of electric field here. As you can see, the component will exist only on this dielectric, you can see here. Okay, now we have assumed the similar surface A, B, C, D cross surface. So if you want to find out a tangential component, so we will use this equation E dot dl is equal to 0, which we have used in this dielectric-dielectric interface. So here no component here, only this component in this dielectric medium. So you can write here that will be equal to, if you want to find out, that is for A, B, C, D, A, E dot dl, if you need to find out so you can write here Et, this component, okay, because this here component, we do not have any component of electric field here. So Et delta W is equal to 0. So it implies that Et is equal to 0. Okay, so tangential component of electric field on a conductor interface, conductor dielectric interface is equal to 0. Now if we need to find out this normal component, okay, so for normal component we'll use this diagram. As you can see, again this electric field inside a conductor is equal to 0. So here we will use what, Gauss law. E dot ds is equal to 0. We know that. Is it 0? No, it is not 0 here. We have assumed that surface which is in dielectric medium. Here this surface is oriented in such a way that some part of this surface is in dielectric medium. So we cannot say that that will be equal to 0. So we can write here that E dot ds is equal to what, q by epsilon. So q is delta s divided by epsilon. And this epsilon is equal to epsilon naught epsilon r. Okay, so what is this E dot ds? So only this normal component exists here. This component dn, that will be like that. So only this component exists here, whose normal is in opposite direction, downward. You can say that. So you can write this E dot ds, that will be equal to what? You can write this in terms of dn. You can also write in terms of en. So I am writing in terms of electric field. You can convert it later. So en delta s is equal to what? Rho s delta s epsilon. Epsilon here is epsilon naught epsilon r. Okay, I have written here epsilon is equal to epsilon naught epsilon r. So that will be cancelled out. So what is E here? This En is equal to rho s epsilon naught epsilon r. So this is the normal component. So normal component of electric field at the conductor and the dielectric interface is equal to what? Surface charge density on the conductor divided by this permittivity of that medium, this dielectric medium. Now if you want to write dn, so you can easily write dn is equal to what? Rho s. You can take it here, the epsilon naught epsilon r, En is equal to dn. So that is also true here. Now let us assume that we have this conductor free space interface. Now for this conductor free space interface, this we can use this. Let us say in place of this dielectric we have free space. Now how it is different from this dielectric? Now if you assume this epsilon r is equal to 1, if this epsilon r is equal to 1, epsilon is equal to epsilon naught, so this dielectric will be considered as a free space. So this is the only difference. So this normal component will be like that. You can write this rho s epsilon naught. So because epsilon r is equal to 1 for this free space. So and this tangential component will be same, no effect on tangential component. That will be equal to 0 for this conductor and free space interface. So this is how this boundary conditions for electrostatics for different interfaces behave. We have studied dielectric, conductor-dielectric, and this conductor free space interfaces. Okay, thanks for watching.